Hello, everyone. How's it going? How is it going, everyone? We are going to listen to more of this and play more of a brief history of time and go forth with it.
Chapter 7. Black Holes Ain't So Black. Before 1970, my research on general relativity had concentrated mainly on the question of whether or not there had been a Big Bang singularity. However, one evening in November that year, shortly after the birth of my daughter Lucy, I started to think about black holes as I was getting into bed. My disability makes this rather a slow process, so I have plenty of time. At that date, there was no precise definition of which points in space-time lay inside a black hole and which lay outside. I had already discussed with Roger Penrose the idea of defining a black hole as the set of events from which it was not possible to escape to a large distance, which is now the generally accepted definition. It means that the boundary of the black hole, the event horizon, is formed by the paths in space-time of rays of light that just fail to get away from the black hole, hovering forever just on the edge. It's a bit like running away from the police and just managing to keep one step ahead but not being able to get clear away. Suddenly I realized that the paths of these light rays could never approach one another. If they did, they must
Hello,
eventually run into one another.
AA01.
It would be like meeting someone
How's it
else
going?
running away from the police in the opposite direction. You'd both be caught, or in this case, fall into a black hole. But if these light rays were swallowed up by the black hole, then they could not have been on the boundary of the black hole. So the paths of light rays in the event horizon had always to be moving parallel to or away from each other. Another way of seeing this is that the event horizon, the boundary of the black hole, is like the edge of a shadow, the shadow of impending doom. If you look at the shadow cast by a source at a great distance, such as the sun, you'll see that the rays of light in the edge are not approaching each other. If the rays of light that form the event horizon, the boundary of the black hole, can never approach each other, the area of the event horizon might stay the same or increase with time, but it could never decrease, because that would mean that at least some of the rays of light in the boundary would have to be approaching each other. In fact, the area would increase whenever matter of radiation fell into the black hole. Or if two black holes collided and merged together to form a single black hole, the area of the event horizon of the final black hole would be greater than or equal to the sum of the areas of the event horizons of the original black holes. This non-decreasing property of the event horizon's area placed an important restriction on the possible behavior of black holes. I was so excited with my discovery that I didn't get much sleep that night. The next day I rang up Roger Penrose. He agreed with me. I think, in fact, that he had been aware of this property of the area. However, he'd been using a slightly different definition of a black hole. He had not realized that the boundaries of the black hole, according to the two definitions, would be the same, and hence so would their areas, provided the black hole had settled down to a state in which it was not changing with time. The non-decreasing behavior of a black hole's area was very reminiscent of the behavior of a physical quantity called entropy, which measures the degree of disorder of a system. It is a matter of common experience that disorder will tend to increase if things are left to themselves. One has only to stop making repairs around the house to see that. One can create order out of disorder. For example, one can paint the house. But that requires expenditure of effort and energy, and so decreases the amount of ordered energy available. A precise statement of this idea is known as the second law of thermodynamics. It states that the entropy of an isolated system always increases, and that when two systems are joined together, the entropy of the combined system is greater than the sum of the entropies of the individual systems. For example, consider a system of gas molecules in a box. The molecules can be thought of as little billiard balls continually colliding with each other and bouncing off the walls of the box. The higher the temperature of the gas, the faster the molecules move. and so the more frequently and harder they collide with the walls of the box, and the greater the outward pressure that they exert on the walls. Suppose that initially the molecules are all confined to the left-hand side of a box by a partition. If the partition is then removed, the molecules will tend to spread out and occupy both halves of the box. At some later time, they could, by chance, all be in the right half or back in the left half, but it's overwhelmingly more probable that there will be roughly equal numbers in the two halves. Such a state is less ordered or more disordered than the original state in which all the molecules were in one half. One therefore says that the entropy of the gas has gone up. Similarly, suppose one starts with two boxes, one containing oxygen molecules and the other containing nitrogen molecules. If one joins the boxes together and removes the intervening wall, the oxygen and the nitrogen molecules will start to mix. At a later time, the most probable state will be a fairly uniform mixture of oxygen and nitrogen molecules throughout the two boxes. This state will be less ordered and hence have more entropy than the initial state of the two separate boxes. The second law of thermodynamics has a rather different status than that of other laws of science, such as Newton's law of gravity, for example, because it does not hold always just in the vast majority of cases. The probability of all the gas molecules in our first box being found in one half of the box at a later time is many millions of millions to one, but it can happen. However, if one has a black hole around, there seems to be a rather easier way of violating the second law. Just throw some matter with a lot of entropy, such as a box of gas, down the black hole. The total entropy of matter outside the black hole would go down. One could, of course, still say that the total entropy, including the entropy inside the black hole, has not gone down, but since there is no way to look inside the black hole, we cannot see how much entropy the matter inside it has. It would be nice, then, if there was some feature of the black hole by which observers outside the black hole could tell its entropy, and which would increase whenever matter carrying entropy fell into the black hole. Following the discovery, described above, that the area of the event horizon increased whenever matter fell into a black hole, a research student at Princeton named Jacob Birkenstein suggested that the area of the event horizon was a measure of the entropy of the black hole. As a matter carrying entropy fell into a black hole, the area of its event horizon would go up, so that the sum of the entropy of matter outside black holes and the area of the horizons would never go down. This suggestion seemed to prevent the second law of thermodynamics from being violated in most situations. However, there was one fatal flaw. If a black hole has entropy, then it ought also to have a temperature. But a body with a particular temperature must emit radiation at a certain time. It's a matter of common experience that if one heats up a poker in a fire, it glows red hot and emits radiation. But bodies at lower temperatures emit radiation too. One just does not normally notice it because the amount is fairly small. This radiation is required in order to prevent violation of the second law. So black holes ought to emit radiation, but by their very definition, black holes are objects that are not supposed to emit anything. It therefore seemed that the area of the event horizon of a black hole could not be regarded as its entropy. In 1972, I wrote a paper with Brandon Carter and an American colleague, Jim Barton, in which we pointed out that although there were many similarities between entropy and the area of the event horizon, there was this apparently fatal difficulty. I must admit that in writing this paper, I was motivated partly by irritation with Bekenstein, who, I felt, had misused my discovery of the increase of the area of the event horizon. However, it turned out in the end that he was basically correct, though in a manner he had certainly not expected. In September 1973, while I was visiting Moscow, I discussed black holes with two leading Soviet experts, Yakov Veldovich and Alexander Starovinsky. They convinced me that according to the quantum mechanical uncertainty principle, rotating black holes should create and emit particles. I believe their arguments on physical grounds, but I did not like the mathematical way in which they calculated the emission. I therefore set about devising a better mathematical treatment which I described at an informal seminar in Oxford at the end of November 73. At that time, I had not done the calculations to find out how much would actually be emitted. I was expecting to discover just the radiation that Zeldovich and Starobostinsky had predicted from rotating black holes. However, when I did the calculation, I found to my surprise and annoyance that even non-rotating black holes should apparently create and emit particles at a steady rate. At first, I thought that this emission indicated that one of the approximations I had used was not valid. I was afraid that if Bekenstein found out about it, he would use it as a further argument to support his ideas about the entropy of black holes, which I still did not like. However, the more I thought about it, the more it seemed that the approximations really ought to hold. But what finally convinced me that the emission was real was that the spectrum of the emitted particles was exactly that which would be emitted by a hot body, and that the black hole was emitting particles at exactly the correct rate to prevent violations of the second law. Since then, the calculations have been repeated in a number of different forms by other people. They all confirm that a black hole ought to emit particles and radiation as if it were a hot body with a temperature that depends only on the black hole's mass. The higher the mass, the lower the temperature. How is it possible that a black hole appears to emit particles when we know that nothing can escape from within its event horizon? The answer, quantum theory tells us, is that the particles do not come from within the black hole, but from the empty space just outside the black hole's event horizon. We can understand this in the following way. What we think of as empty space cannot be completely empty, because that would mean that all the fields, such as the gravitational and electromagnetic fields, would have to be exactly zero. However, the value of a field and its rate of change with time are like the position and velocity of a particle. The uncertainty principle implies that the more accurately one knows one of these quantities, the less accurately one can know the other. So in empty space, the field cannot be fixed at exactly zero, because then it would have both a precise value, 0, and a precise rate of change, also 0. There must be a certain minimum amount of uncertainty, or quantum fluctuations, in the value of the field. One can think of these fluctuations as pairs of particles of light or gravity that appear together at some time, move apart, and then come together again and annihilate each other. These particles are virtual particles like the particles that carry the gravitational force of the sun. Unlike real particles, they can't be observed directly with a particle detector. However, their indirect effects, such as small changes in the energy of electron orbits in atoms, can be measured and agree with the theoretical predictions to a remarkable degree of accuracy. The uncertainty principle also predicts that there will be similar virtual pairs of matter particles, such as electrons or quarks. In this case, however, one member of the pair will be a particle and the other an antiparticle. The antiparticles of light and gravity are the same as the particles. Because energy cannot be created out of nothing, one of the partners in a particle-antiparticle pair will have positive energy and the other partner negative energy. The one with negative energy is condemned to be a short-lived virtual particle, because real particles always have positive energy in normal situations. It must, therefore, seek out its partner and annihilate with it. However, a real particle close to a massive body has less energy than if it were far away, because it would take the energy to lift it far away against the gravitational attraction of the body. Normally, the energy of the particle is still positive, but the gravitational field inside a black hole is so strong that even a real particle can have negative energy there. It is therefore possible, if a black hole is present, for the virtual particle with negative energy to fall into the black hole and become a real particle or antiparticle. In this case, it no longer has to annihilate with its partner. Its forsaken partner may fall into the black hole as well, or having positive energy, it might also escape from the vicinity of the black hole as a real particle or antiparticle. To an observer at a distance, it will appear to have been emitted from the black hole. The smaller the black hole, the shorter the distance the particle with negative energy will have to go before it becomes a real particle, and thus the greater the rate of emission and the apparent temperature of the black hole. The positive energy of the outgoing radiation will be balanced by a flow of negative energy particles into the black hole. By Einstein's equation, E equals mc squared, where E is energy, m is mass, and c is the speed of light, energy is proportional to mass. A flow of negative energy into the black hole therefore reduces its mass. As the black hole loses mass, the area of its event horizon gets smaller, but this decrease in the entropy of the black hole is more than compensated for by the entropy of the emitted radiation, so the second law is never violated. Moreover, the lower the mass of the black hole, the higher its temperature. So as the black hole loses mass, its temperature and rate of emission increase, so it loses mass more quickly. What happens when the mass of the black hole eventually becomes extremely small is not quite clear, but the most reasonable guess is that it would disappear completely in a tremendous final burst of emission equivalent to the explosion of millions of H-bombs. A black hole with a mass a few times that of the Sun would have a temperature of only 1/10,000,000th of a degree above absolute zero. This is much less than the temperature of the microwave radiation that fills the universe, about 2.7 above absolute zero, so such black holes would emit even less than they absorb. If the universe is destined to go on expanding forever, the temperature of the microwave radiation will eventually decrease to less than that of such a black hole, which will then begin to lose mass. But even then, its temperature would be so low that it would take about a million years, one with 66 zeros after it, to evaporate completely. This is much longer than the age of the universe, which is only about 10 or 20,000 million years, 1 or 2 with 10 zeros after it. On the other hand, as mentioned in Chapter 6, there might be primordial black holes with a very much smaller mass that were made by the collapse of irregularities in the very early stages of the universe. Such black holes would have a much higher temperature and would be emitting radiation at a much higher rate. A primordial black hole with an initial mass of 1,000 million tons would have a lifetime roughly equal to the age of the universe. Primordial black holes with initial masses less than this figure would already have completely evaporated, but those with slightly greater masses would still be emitting radiation in the form of X-rays and gamma rays. These X-rays and gamma rays are like waves of light, but with a much shorter wavelength. Such holes hardly deserve the epithet black. They really are white hot and are emitting energy at a rate of about 10,000 megawatts. One such black hole could run 10 large power stations if only we could harness the power. This will be rather difficult, however. The black hole would have the mass of a mountain compressed into less than a millionth of an inch, the size of the nucleus of an atom. If you have one of these black holes on the surface of the Earth, there would be no way to stop it from falling through the floor to the center of the Earth. It would oscillate through the Earth and back until eventually it settled down at the center. So the only place to put such a black hole in which one might use the energy that it emitted would be in orbit around the Earth. And the only way that one could get it to orbit the Earth would be to attract it there by towing a large mass in front of it, rather like a carrot in front of a donkey. This doesn't sound like a very practical proposition, at least not in the immediate future. But even if we cannot harness the emission from these primordial black holes, what are our chances of observing them? We could look for the gamma rays that the primordial black holes emit during most of their lifetime. Although the radiation from most would be very weak because they are far away, the total from all of them might be detectable. However, this background could have been and probably was generated by processes other than primordial black holes. One can therefore say that the observations of the gamma ray background do not provide any positive evidence for primordial black holes, but they do tell us that on average there cannot be more than 300 in every cubic light year in the universe. This limit means that primordial black holes could make up most 1/1,000,000th of the matter in the universe. With primordial black holes being so scarce, it might seem unlikely that there would be one near enough for us to observe as an individual source of gamma rays, but since gravity would draw primordial black holes toward any matter, They should be much more common in and around galaxies. So although the gamma-ray background tells us that there can be no more than 300 primordial black holes per cubic light year on average, it tells us nothing about how common they might be in our galaxy. If they were, say, 1 million times more common than this, then the nearest black hole to us would probably be at a distance of about 1,000 million kilometers, or about as far away as Pluto, the farthest known planet. At this distance, it would still be very difficult to detect the steady emission of a black hole, even if it was 10,000 megawatts. In order to observe a primordial black hole, one would have to detect several gamma-ray quanta coming from the same direction within a reasonable space of time, such as a week. Otherwise, they might simply be part of the background. But Planck's quantum principle tells us that each gamma-ray quantum has a very high energy because gamma rays have a very high frequency. So it would not take many quanta to radiate even 10,000 megawatts. And to observe these few coming from the distance of Pluto would require a larger gamma-ray detector than any that have been constructed thus far. Moreover, the detector would have to be in space because gamma rays cannot penetrate the atmosphere. Of course, if a black hole as close as Pluto were to reach the end of its life and blow up, it will be easy to detect the final burst of emission. But if a black hole has been emitting for the last 10 or 20,000 million years, the chance of it reaching the end of its life within the next few years, rather than several million years in the past or future, well, it's really rather small. So in order to have a reasonable chance of seeing an explosion before your research grant ran out, you would have to find a way to detect any explosions within a distance of about 1 light year. You'd still have the problem of needing a large gamma-ray detector to observe several gamma-ray quanta from the explosion. However, in this case, it would not be necessary to determine that all the quanta came from the same direction. It would be enough to observe that they all arrived within a very short time interval to be reasonably confident that they were coming from the same burst. One gamma-ray detector that might be capable of spotting primordial black holes is the entire Earth's atmosphere. We are in any case unlikely to be able to build a larger detector. When a high-energy gamma-ray quantum hits the atoms in our atmosphere, it creates pairs of electrons and positrons, anti-electrons. When these hit other atoms, they in turn create more pairs of electrons and positrons, so one gets what is called an electron shower. The result is a form of light called Tranquil radiation. One can therefore detect gamma-ray bursts by looking for flashes of light in the night sky. Of course, there are a number of other phenomena, such as lightning and reflections of sunlight off tumbling satellites and orbiting debris that can also give flashes in the sky. One could distinguish gamma-ray bursts from such effects by observing flashes simultaneously at 2 or more fairly widely separated locations. A search like this has been carried out by 2 scientists from Dublin, Neil Porter and Trevor Weeks, using telescopes in Arizona. They found a number of flashes, but none that could be definitely ascribed to gamma-ray bursts from primordial black holes. Even if the search for primordial black holes proves negative, as it seems it may, it will still give us important information about the very early stages of the universe. If the early universe had been chaotic or irregular, or if the pressure of matter had been low, one would have expected it to produce many more primordial black holes than the limit already set by our observations of the gamma-ray background. Only if the early universe was very smooth and uniform with a high pressure, can one explain the absence of observable numbers of primordial black holes. The idea of radiation from black holes was the first example of a prediction that depended in an essential way on both the great theories of the century, general relativity and quantum mechanics. It aroused a lot of opposition initially because it upset the existing viewpoint. How can a black hole emit anything? When I first...
Okay, guys, just a second. We're going to take a moment in this, just a second.
Announced the results of my calculations at a conference at the Rutherford Appleton Laboratory near Oxford, I was greeted with general incredulity. At the end of my talk, the chairman of the session, John G. Taylor from King's College London, claimed it was all nonsense. He even wrote a paper to that effect. However, in the end, most people, including John Taylor, have come to the conclusion that black holes must radiate like hot bodies if our other ideas about general relativity and quantum mechanics are correct. Thus, even though we have not yet managed to find a primordial black hole, there is fairly general agreement that if we did, it would have to be emitting a lot of gamma rays and X-rays. The existence of radiation from black holes seems to imply that gravitational collapse is not as final and irreversible as we once thought. If an astronaut falls into a black hole, its mass will increase, but eventually the energy equivalent of that extra mass will be returned to the universe in the form of radiation. Thus, in a sense, the astronaut will be
That's
recycled.
really interesting.
It will be a poor sort of immortality, however, because any person or personal concept of time for the astronaut would almost certainly come to an end as he was torn apart inside the black hole. Even the types of particles that were eventually emitted by the black hole would in general be different from those that made up the astronaut. The only feature of the astronaut that would survive would be his mass or energy. The approximations I used to derive the emissions from black holes should work well when the black hole has a mass greater than a fraction of a gram. However, they will break down at the end of the black hole's life when its mass gets very small. The most likely outcome seems to be that the black hole will just disappear, at least from our region of the universe, taking with it the astronaut and any singularity there might be inside it, if indeed there is one. This was the first indication that quantum mechanics might remove the singularities that were predicted by general relativity. However, the methods that I and other people were using in '74 were not able to answer questions such as whether singularities would occur in quantum gravity. From 1975 onward, I therefore started to develop a more powerful approach to quantum gravity based on Richard Feynman's idea of a sum over histories. The answers that this approach suggests for the origin and fate of the universe and its contents, such as astronauts, will be described in the next two chapters. We shall see that although the uncertainty principle places limitations on the accuracy of all our predictions, it may at the same time remove the fundamental unpredictability that occurs at a space-time singularity.
All right, that's that chapter.
Chapter 8.
All right, so we have 2 hours left of this audiobook. So essentially we have 2 more episodes left of this audiobook live stream thing. Just a second. So now we can spend the rest of the time talking. Hello everyone, how's it going? Alright, there we go. So yeah, they were talking about how in a black hole, if you were an astronaut and you got sucked into a black hole, you would be recycled into radiation, and that radiation would go outward into the universe, and all of your mass and everything that you are would be completely disintegrated. Now, just a second guys, I have to turn down this music. That would be terrible for me specifically. For me, I'm so important to where my body needs to be preserved. Right? Like, I'm so important that, you know, it needs to be safe. It needs to be safe, right? Just it is what it is. So if you were an astronaut, if I was an astronaut and I got sucked up into a black hole, you would never see me ever again. Right? Because I would be turned completely into radiation. I would even argue that your soul probably turns into radiation. I would argue that space is so unforgiving that if you get sucked into a black hole, then your soul gets sucked into. I'm certain. I mean, think of how brutal space is. But yeah, alright, I'm done smoking now. But yeah, think about it. And then he was talking about, it was more about space and protons and, Pluto, how, you know, if certain hypotheses were correct, then it would argue that there was a black hole near Pluto or something. I don't know. I'm gonna look back at all of this and discuss it later. I'm gonna listen to all of the footage, and then I'm gonna make a comprehensive video. I'm gonna make it in a few months though, because I just need to listen to the footage over and over again. That's why I'm making this audiobook, is so I can listen to the audiobook and have something to look at, like playing a video game. But we have 2 more episodes left of this installment. And I'm not gonna leave yet. Just a second, guys. Oh, that one is too hard. I'm not doing that one. Right, guys? But anyway, I just wanted to say that I'm grateful for absolutely everything. You guys are looking at a future rock star. You know, I have a whole music career ahead of me. Just a second, I keep lagging. I just wanted to say that I'm grateful for a future rock star. Yeah, I'm grateful for everything. I'm grateful for everything. I'll never complain. I'm grateful to these giant media corporations. I'm grateful to YouTube. I'm grateful to Universal. I'm grateful to Sony. I'm grateful to Disney. I'm grateful to Paramount. I'm grateful to HBO. I'm grateful to MTV. I'm grateful to all sorts. To all sorts of people. I'm grateful to fast food companies. I'm grateful to theater companies. I'm thankful. Guys, you've given me love, you've given me power, you've given me all sorts of things. I'm grateful. You gave it to the right person. Oh man. I don't even know how the hell that happened so quickly like that. You mess with one of them, you mess with them all. Yeah, we're getting out of here. But yeah, guys, I'm grateful. I'm grateful for everything. I'm grateful to the military. I'm grateful to the Navy. I'm grateful to the Army. There's so many people I could be grateful to. There's particular people that I'm grateful to. I'm grateful to old men who always look out for me because they know I'm the right choice. They know I'm the right choice for many different things. They know because they know everything. So I have nothing to complain about. I'm in like a brotherhood kind of like way thinking where I want to help my fellow man, especially people who are worthy of heaven. I'm like that. There's little boys that I wanna sing for that have things going on with their health. There's kids that I want to read stories for. It is what it is. I am grateful for absolutely everything. Okay? I am grateful for everything. Okay, and I'm not complaining. And I'll always do good by the scientific community and the paralegal community. Not paralegal. Whatever it means to be a police officer. I'll do whatever. I'll listen to them. You all should listen to them too. They're the servants of the nation. They're first responders. You should take in what you can get, make the right decisions. Use Grok. Use Grok. If you need to use AI, use Grok. I'm begging you. Alright, guys. So I'm just gonna drive around in this thing for a little bit. But yeah, guys, I'm grateful for everything. I really can't complain. There's really not much to complain about. Right? I want to get fit. I want to learn guitar. I want to learn saxophone. I want to meet women. Like, I want to spend time with women, right? I love women. Guys, I love women. Who doesn't? That's the thing. I pretend that I don't. I pretend that I don't need them because I love them so much. Alright? I need them. Yeah. But I'm just a simple man. I need woman. It's just as simple as that. Other than that, guys, I'm gonna let you go. I know I didn't get many views this time around. It's okay. I really just want to get through this book. I'm probably gonna get through the whole thing today. I'm probably gonna stream more than once. But yeah, there's 2 hours left, and it's a good book. I'm learning a lot from it, and I'm gonna listen to it over and over again through these YouTube videos. And my sponsor loves it. My sponsor loves it when I listen to science articles and science books. So I'm gonna try and sound smart for him. I'm really not as smart as him. Really, I'm not. He's an intellectual beyond comprehension. I'm just you know, it's really hard to explain, and I don't really want to get into it because it's really like a tender thing. But me and him definitely we need each other forever. So I don't want anything from him besides just his companionship. And if people hate it when I talk about this, but without him, I would be absolutely nothing. Right? Without him, I wouldn't have these women in my life. I wouldn't have any of this. And nothing. I wouldn't have anything. Can you guys believe that? Oh my goodness! What do you do for someone that I've cried thinking about this, like a lot. I've cried thinking about this a lot. So yeah, I'm very grateful. I'm very grateful. Alright guys, just know I'll always pull through for my bosses. So the goal is to get to become old. Really old. Really old. And then live a full life, and then have your family take care of you, and then yeah, that's pretty much it so far. That's pretty much all that needs to be briefed. Okay guys, I love my girlfriend, I love my wife, I love my girlfriend, I love my redheaded girlfriend. I really can't talk about much of my personal life here, other than I'm grateful.